Hello students, today we're going to cover the next part of the module number 4, which is moment of inertia. Let us understand before to it, there are some of the things which I need to take a reference from a centroid, which is a part of in the part of calculation of a moment of inertia. So what is actually meant by moment of inertia over here is that with reference to the centroid, in the centroid part, we have calculated the x bar, that is x bar is equal to summation of all areas into distance divided by summation of complete area, that is nothing but all area added together and areas of small areas and their respective distance with respect to the axis with which we used to calculate the x bar. What was the x bar? Was actually the distance of a centroid with respect to the any reference axis. Okay, so the x distance, the horizontal distance, was being calculated over here. So in this one, moment of inertia, this has been given as, it is also called as second moment of area. Moment is nothing but force into distance. That is what we have it here. That is F into D is nothing but a moment. But when we were calculating in the centroid, we used to multiply areas into distance. That's what we call it as moment of area. Okay, here what we do in moment of inertia is that it is nothing but second moment of area, which is actually we multiply area, we actually multiply area into distance, so we get moment of area again into distance, with which we used to calculate the moment of inertia. So moment of inertia, why we called it second moment of area, is nothing but we multiply the moment of area. Moment of area is area into distance, and second moment of area is nothing but area into distance. So it becomes distance square. So moment of inertia is actually nothing but second moment of inertia, which is given second moment of area, which is given as a into x square. What we can write it for this one. Okay, so this is one of the important element in calculating the geometrical properties of the area. This finds most important segments when we use any of the section for when it is being used for the many other purpose, in the form of like when we want to apply a force in the major axis and minor axis of the components, we should be able to understand how much load it can take. So calculating that value will be helpful for us with the help of moment of inertia. And now let us get into how we can calculate the moment of inertia for plane areas. We can see over here, I have taken a very small element, very small area. Just you can see to here, this is a very small area. That area, okay, in from that area I take a very small segment of the area of that area. So that means I have taken one area. In that area I have taken one small element. I mention that one as dA. Okay, and the complete area is represented as area. You can see over here, this has been shown over here. Okay, so this small area, that dA, is at a distance of x from the origin. You can see the origin over here. This is the origin. We have x axis in this direction and y axis in this direction. Okay, so this is the point where we are supposed to find it. This is a point of reference as a origin for us, this one. Okay, now with respect to that, if I want to calculate the moment of inertia along the x direction, this is the x direction what we have it. The x direction is along this line. So this one x I take it as x direction. So if I want to calculate the moment of inertia of the small element dA, the small element dA which has been shown here. Okay, so small element dA, okay, which is shown here. So the moment of inertia of that element along this x axis is given as, which is over here, you can see it. So this is small dixx. Moment of inertia is represented as ixx, or ixx in the sense, if we are calculating along the xx direction, we mention it as ixx. If you want to calculate in y direction, we mention it as Iyy. So it is d, as it is for the small element dA, we calculate that moment of inertia d into Ixs, which is equal to, I said to you that area into distance square. So same way you can see it over here. So area of that small element is, area of the small element is dA, and distance you can see over here, distance over here from the y-axis, from here to here, this distance, what we have it as a y. Okay, so y into square of it. So area into distance is moment of area, but moment of inertia is area into distance into distance. So it becomes area into distance square. So as per the definition of the moment of inertia. So in that case, we are getting this equation, that is y square, we are getting this equation as y square into dA. Okay, now if I want to calculate the moment of inertia of the entire segment which is given as complete area A. Okay, so for the complete area, if I want to calculate, as it is a very small segment dA, I want to calculate for the entire segment area A. So what I need to do, if I want to go from a smaller part to higher part, we need to integrate. So that's what I am doing it over here. I integrate this equation, this equation on either side. So I get, instead of dIxx, the small element, it becomes Ixx. And on the right side, we take it as integration of y square into dA. That means if we want to calculate the moment of inertia of any segment, we can calculate using this equation, that is integration of y square into dA. And in the same line, if we want to calculate along the y direction, that is being given over here, this is y and this is y, and the distance over here, you can have a look, the distance is x. So distance of the small element dA with respect to the axis yy is x. So we get Iyy is equal to area of the small element dA into distance square of it, that is x square, and doing the integration as I wanted for the complete area. So it becomes around x square into dA integration of it. Now I have taken an axis in x direction, I have taken an axis in x direction, I have taken the axis in y direction. There is one more axis, that is z direction. So that what we call it as, also call it as polar moment. So polar coordinates. So with respect to the polar coordinate which is there at this point, which is actually presently this sketch what we have taken on here, it's a 2D sketch. This is a 2D sketch. The sketch what we have taken is the 2D sketch, and the z axis is perpendicular to the screen. So that means which is not visible to us, it is over here. So with respect to the z axis, the distance which is being given over here is r, you can see over here. So in the same line, if we want to calculate the moment of inertia that is along the polar coordinates, that is polar moment of inertia, what we call it as, about zz axis, which is nothing but distance of that axis, which is r, into area of that into again distance. So it becomes dA, the area for this one. Okay, area for that one, and the distance square of it, integration will going to give us the moment of inertia. Now we have understood that from this part of it, that moment of inertia is nothing but area into distance square. Okay, so with which we'll go into the next segment of it, that is radius of gyration. So radius of gyration have many more applications. Just remember one thing, if they tell you, as per the examination point of view, if they tell you to find out the radius of gyration of the standard section, they're going to ask in the examination, calculate the radius of gyration for the section shown in the figure. That means first you're supposed to calculate the equation for that radius of gyration is given as it is nothing but kxx. If you want to calculate for the along the horizontal xx direction, it is integration of Ixx divided by area. And if you want to calculate for the yy direction, we need to take it as square root of square root of Ixx divided by area, and kyy is given as square root of Iyy divided by area of this one. So this explanation for the radius of gyration is being given over here. Just have a look. This is not that much important. I'm not going in detail for this one, otherwise the video becomes too much lengthy. So we come to the next part of it, which is very important for us. That is two theorems. So one is over here we can see it is perpendicular axis theorem, and the second one is parallel axis theorem. Axis theorem and parallel axis theorem. So let me tell you one thing over here at this point of time, that in the examination, as in module 4, there will be two options. The first option, so one question will be asked, there is another option or option for you, wherein you can opt one of them to answer that module. Okay, so what I want to tell you over here is, at this point of time, the question, one theory question will be asked from the moment of inertia, or another will be a problem. So the derivation which will be asked for the examination, the standard derivation, I've told you about this one in the previous segment of a centroid also. One derivation from the centroid and one derivation from the moment of inertia will going to turn up in the examination. Also, along with this one, in the moment of inertia, there are two theorems which has been found repeated place in the question paper. So that is perpendicular axis theorem and the parallel axis theorem. And the out of these two, the one which has been frequently asked is parallel axis theorem. Okay, so taking the point into consideration, let me tell you one thing over here, that one out of these two one theorem will go definitely turn up in the examination, or it might be a derivation of a moment of inertia for the standard sections. Okay, and one problem will be asked. Okay, to there is also a shuffling. They're going to ask one problem from the centroid and the derivation from the moment of inertia, or a theorem from the moment of inertia. That will be one kind of cases. The other case might be like they will going to ask the derivation for the centroid and the problem from moment of inertia they will going to ask. So we have to get prepared for all kind of questions which will be asked in the examination. So perpendicular axis theorem. Now come back over here, that is perpendicular axis theorem. What is meant by this perpendicular axis theorem? It states that moment of inertia of an area about an axis perpendicular to its plane, that is polar moment of inertia, at any point is equal to the sum of the moment of inertia about any two mutually perpendicular axes through the same point in the plane of the area. So what it want to tell you here, I said to you here, is that so we have three axes, that is x, y and z. So the polar moment of inertia, that means if we have any area with respect to that, if I take the distance as r, okay, so distance r is with respect to the z. So with respect to the z, what we have it from the origin. Okay, so this moment of inertia of any section with reference to point O is equal to, so how we write the moment of inertia along the polar moment of inertia direction, that is IZZ. So what it want to tell you over here is that, so polar moment of inertia, that is IZZ, is equal to sum of the moment of inertia of the same section along the two mutually perpendicular direction, that is Ixx plus Iyy. That means the moment of inertia along the polar moment of direction should be equal to sum of these two, that is Ixx plus Iyy of the same section. So that what we have it in the derivation also. Okay, so for that we consider an area that is which is given as A. So in xy plane, so x is this direction, in y in this direction, the x and y plane, it has been considered a small area as shown in the figure. The polar moment inertia about zz passing through O, that means passing from O, the polar, that is z. So through O is given as, which is given as with this equation. This equation we have derived it before, that is Ixx along the polar moment of inertia, that is Izz, should be equal to integration of r square into dA. The reason of integrating is that because it's a small area dA, so that's the reason if you want for the larger area, that is capital A, that is being given over here for the capital A, this becomes integrated part. Okay, so now the izz is equal to integration of r square into dA. But come back over here. So we know that with respect to the Pythagoras theorem, so the distance over here, distance for this same element area, okay, along the x direction it is x, along the y direction it is y, this is the distance, and the polar direction is r. So we can see this is a, by applying this one Pythagoras theorem, we know that r square, that is equal to x square plus y square. So once we apply this one over here, you can see that, so this part, just I substitute in place of r square x square plus y square. So in the next step we can see there is x square plus y square has been substituted in place of r square. So izz is equal to integration of x square plus y square into dA. I just separated out this x square into dA and y square into dA. When I separate these two segments with a positive sign in between them, I know that integration of integration of x square into dA is nothing but ixx, and integration of y square into dA is nothing but Iyy. So once I substitute that, which is actually nothing but, so integration of x square into dA is Iyy, and integration of y square into dA is Ixx. So just we have seen it here in my notes above. Just see it here. This we know that these three segments, that what I am substituting in this one, and we get this part, which is nothing but our perpendicular axis theorem statement itself, which is nothing but izz is equal to ixx plus iyy. So hence proof. This is the only small theorem what we have it. So that what I said, just statement for this one, and a proof what we are supposed to do it for that. Okay, we go with the next part of it. We go to the next part of it, that is parallel axis theorem. Okay, coming back to the parallel axis theorem, it states that moment of inertia of any areas about an axis in its plane is sum of the moment of inertia about a parallel axis passing through the centroid of an area and the product of area and the square of the distance between them, the two axes. The statement is much larger. We can frame it down in a very simple manner. What it want to tell you here is that if you want to calculate the moment of inertia about any axis over here, any axis means which is somewhere it has been shown over here. Just have a look. The axis has been shown over here, which is represented as AB. Okay, what it want to tell you is that there is an area. You want to calculate the moment of inertia about the axis AB of that area. So it is been given as A, that is moment of inertia. I know I have told you before that if you want to calculate moment of inertia, it is represented as I, and at what axis you are calculating, xx, xyy, or AB. Presently we have taken AB, so it has been represented as IAB is equal to moment of inertia about its centroidal axis. That means the section has the centroid, which is represented as GU here at the center, and we should try to take the axis which should be parallel to AB. So that means we should take an axis which should be passing from the centroid but parallel to the axis at which we are calculating. We are calculating at the axis AB. So the other axis what we are supposed to take passing from the centroid but should be parallel to AB. So that what I have taken XX, which is parallel to AB. Okay. So IAB is equal to IXX, that is moment of inertia of that section passing along the centroid. Okay, plus area of the section into distance between the two axes. Just have a look. The distance between XX and AB is given as D. XX and AB has been given over here and it is D. Okay, so it becomes IAB, that is moment of inertia about the axis AB, is equal to IXX, that is moment of inertia about the centroidal axis, plus area into area of the section into distance between the two axes. The distance between two axes is nothing but axis at which where we are calculating AB and axis which is passing from the centroid and parallel to AB. Okay, the distance between them is D, so that is equal to D square. So this is a statement what we have it for the parallel axis theorem. So we're going to prove this one. So I have explained to you what is the statement. So we go to the next part, that is what we have is the area. To prove in this one, just have a look. There is an area what is being taken. So there is an area what is being taken over here. Okay. So this area what we have taken over here. Of that area, we have taken an axis AB. We have taken an axis at AB over here at the bottom side, and we have made sure that there is an axis which is passing from the centroid and also should be parallel to AB as per the statement. Okay, and before we calculate, we take very small strip that is given over here. So there is a small strip of DA. Just have a look. This sketch have been highlighted down over there. So which is given as DA. Okay, so element has been noted down as DA over there. So consider an element area DA parallel to XX axis. That XX axis is along the centroidal axis. Let Ixx, that is moment of inertia of that area of the element what we have taken along its centroidal axis. The centroidal axis, what we call, actually we call centroidal axis because it is passing from the centroid. That is Ixx. We represent this Ixx which is passing as equal to Ig. What is the reason? G is nothing but centroid. So XX axis what we have taken which is passing from the centroid has been given as Ig, that is moment of inertia about XX axis. Okay, so then IAB is nothing but moment of inertia about the reference axis AB, that is IAB along this axis AB. Okay, so area of the AA is equal to capital A is given as area of the body. D, small d, just have a look here. This small d is the distance between this axis and the bottom axis, AB and XX. Okay, so moment of inertia has been done. So moment of inertia of the element AB. So we know as per the definition of a moment of inertia, that is area into distance square. So now as presently we are taking only for the small strip dA. So that's the reason the moment of inertia of this small element dA about this AB axis should be equal to, that is I, as it is small element DIAB. So DIAB is equal to, so as per the definition it is area into distance square. So the distance of that small element with respect to the axis is given as y plus d. So that is nothing but y plus d. Okay, where why I have taken a y over here, it is the distance of xx axis. It is the distance of that small element with respect to the centroidal, and from this centroid it is d. Okay, so just have a look here. So both have been given here on this side. So y plus d. So distance of that small element dA with respect to this axis is nothing but y plus d and square of that as per the definition of the moment of inertia. Okay, so that's what I have taken it over here in this calculation. Moment of inertia about AB is equal to, moment of inertia of AB is equal to, so that is small dA into d into y whole square of it. Now as it is only for the small segment dA, if you want to calculate for the entire segment, that is this entire area about this axis, so we need to do the summation of all this dA. So I have taken summation of that. So just have a look, this summation of all this one, summation of dA into y plus d whole square of it. We know that a plus b whole square is equal to a square plus b square plus 2ab. So I'm going to expand this part y plus d whole square as y square plus d square plus 2 into d into y. So keeping the summation of dA as it is, and then respectively multiply this segment with the dA. we're going to get the next part, that is, so summation of, just have a look with this equation. Okay, summation of dA into y square plus summation of dA into d square plus summation of dA into d into y. So out of this one, this they're going to give us the equation for the moment of inertia about axis. Now that the first part, that is summation of dA into y square. So that is actually nothing but moment of inertia about Rx Ixx. So you can see what is the definition for the moment of inertia. A moment of inertia is nothing but area into distance square. So that summation of dA is the area, into distance between Ix axis with respect to that area is given over here. So it is y. So that is nothing but this segment will become Ixx. Okay, so it is being given over here. So this is actually nothing but what we have it. This is actually Ixx. Okay, then come to the next part of it. So the next part what we have it over here is this part. Okay, this one, summation of dA into d square. Summation of all dA, that is summation of all the small strip added together, it will going to formulate actually summation of all dA is actually nothing but complete area. So that means we're going to substitute that value, that is summation of, we're going to have summation of dA into d square is actually nothing but is equal to, this is area, that is A, into, we keep d square as it is, that is the distance between the two axes xx and AB. Okay, so that have been kept. Come to the last segment of it, this one, that is 2 is a constant, I keep it outside. I want that main part, that is dA. I'll just keep dA into y first and the distance d at the last. But we know that this part dA into y. dA is the area of the small element, y is the distance of that axis with respect to xx axis. So we were discussing about the summation of dA into y into d. So we'll come to this part, that is dA into y. We know that the area of that small element into distance y is a moment of the area. Okay, so and if we enlarge it for the entire area, that is for this entire area, as we have taken only the small element, I just draw it bigger one to understand for you all. Okay, so if I take this larger area and we have taken only for the small strip and along the x axis which is passing from the centroid G. Okay, and we know this distance. When we take complete area altogether, this distance what we have taken as y, it get reduces to 0. That means it get overlapped, it get overlap along the axis itself. Okay, so it is initially y. So when we go on taking the areas, that is bottom areas, top area, so this goes on reduces and it get overlap along the same line. So then y distance becomes 0. So y distance becomes 0 means, in that sense, that is summation of dA into anything, that is y which is equal to 0 now. So then area, a moment of this area and this one, this complete part becomes, as we are multiplying with 0, this complete part becomes 0. That means it get deleted. So what is left out? I explained to you that it is nothing but IAB, which is as it is, which is equal to, and I is equal to Ixx plus area into distance square. Okay, so that means when we take this part and get represented over here, has been answer for this one have been represented over here. So this is the part with which we have found the proof of the parallel axis theorem. So this is the first segment of which we're going to cover the next segment of the derivation of the standard segment in the next lecture. Thank you.